Hello everyone. Now today let us see the laws of photochemistry. Here we shall take the principle of the colorimeter or the colorimetric analysis. Now in the analytical method, for the determination of the concentration of the substance based on the intensity of the color of the solution, this colorimeter instrument is used. So basically, when the electromagnetic radiations are passed through the colored solution, some of the light are absorbed by the colored solution as per the intensity of the color of the solution, while the remaining radiations are transmitted through that solution, and hence we can determine the absorbance and the transmitted radiation, and ultimately we can determine the concentration of the substance or the solution of the given sample. So there are two laws that governs the absorption of light by the molecules, Lambert's law and Beer's law, and the photochemistry is based on the Beer-Lambert's combined law. Let us see the first law, Lambert's law. Lambert's law gives the relationship between the intensity of the absorbed light and the transmitted light. This was given by first Lambert in 1760 and was extended by Beer in 1852. Lambert law indicates the relation between the absorbed light and the thickness of the medium. So it states that the Lambert law states that when a monochromatic beam of light passes through a homogeneous absorbing medium, equal fractions of the incident radiations are absorbed by the successive layer of equal thickness of the light absorbing substance. So it means that the thickness of the medium is important in this case. Here the absorption of the light occurs by the equal fractions or the successive layers of the equal thickness of the medium. Let us understand this by another statement. Say Lambert's law can be stated as the rate of decrease of intensity with the thickness of the absorbing medium is proportional to the intensity of the penetrating or incident radiation. So some incident radiations we have passed into the colored solution, there is the decrease in the intensity of that absorbed radiation because the solution is colored and it absorbs some of the radiations, and the radiations coming out will be less compared to the incident radiation. So there is a decrease in the intensity with the thickness of the absorbing medium. So it depends on the path length, or we say the thickness of the medium. So we define or we state the Lambert law as when a monochromatic beam of light passes through a homogeneous and transparent medium, keeping the concentration of the solution constant, the rate of decrease in intensity of the transmitted light with the thickness of the medium is directly proportional to the intensity of the incident light. See, we can understand this by a diagram as shown here. This is a cuvette or a sample holder that we take. The incident radiations are passed here I0 or I0, and the transmitted light is coming out from the right side. So this is shown by I. This is the path length or the thickness of the medium, which is denoted by T. So considering this and comparing this with the another sample holder or the cuvette, see if the sample holder is having the path length of this much centimeter, okay, so this may be around 2 centimeters, this may be around 5 centimeters. So as the thickness of the medium or the path length is increased, the absorbance of the radiation will also get increased, because if we see there are such molecules shown in case of the first cuvette and the number of molecules which are present in the second cuvette, second sample holder will be more, because the area increases and the thickness increases. So molecules present also increases, and hence the absorbance of the radiation will ultimately increase. So we say the decrease in the rate of the intensity of the radiation with the thickness of the medium is directly proportional to the intensity of the radiations. So this is shown by a equation given, minus because it is a decrease in the intensity of the radiation with the thickness of the medium. So minus di by dt, which is proportional to the intensity of the incident radiation. So it is I. So according to Lambert, we get the first equation as minus di by dt is proportional to I. Now removing the proportionality sign, we get minus di by dt is equal to k1 into I, where k1 is the proportionality constant, or we say it is an absorption coefficient or extinction coefficient. I is the intensity of the incident light, and T is the thickness of the medium. Here the negative sign, as we have discussed, it indicates the decrease in the intensity of light. This we can understand that when we pass the radiation, as it gets absorbed by the sample present colored solution, the intensity of the radiation coming out will be less. So it decreases with the thickness of the medium as some of the light gets absorbed. So taking similar terms on one side, we get minus di by I is equal to k1 into dt. Now integrating this equation 2 with the limits, within the limits, that is at say thickness 0 to thickness t. See, integration means taking the whole system, all the limit into consideration as a whole of the system. So starting from 0 to t thickness and the intensity of the radiation I0 to IT that is transmitted, within this limits it defines the whole system, and we integrate the equation number 2. So we get integration from the limit I0 to IT di by I is equal to k1 integration 0 to t of dt. I is integrated from the limit it to I0. So we get ln it minus ln I0. But we know, as per the rules, like ln of A minus ln of B is equal to ln of A upon B. Okay. So that gives ln it by I0 minus of that is equal to k1 into t, because here we get k1 into t minus 0. So it is k1 into t. So we can write this as ln it by I0 is equal to minus k1 t, taking negative sign on the opposite direction. So it by I0 is equal to e raised to minus k1 into t. When we take the natural logarithm on the right side, it becomes e to the power of the term which is present on the right side. So we can remember that ln natural log, if we take on the right side, it gives e to the power of that term. Say for example, it is ln x is equal to 2. So x will be equal to e to the power 2. Okay. Removing ln, we get e to the power the term present on the right side. So rearranging the terms, we get it is equal to I0 into e raised to minus k1 t. This is the mathematical expression of the Lambert's law. Okay. Also, the Lambert's law can be expressed as it is equal to I0 into 10 to the power minus k dash t. This equation we get, or this expression is obtained by converting the natural logarithm into log, as we have the equation ln it by I0 is equal to minus k1 t. Now if we convert ln into logarithm term, natural log to logarithm term, we get 2.303 into log it by I0 is equal to minus k1 t. Okay, when we want to convert natural log into log, we multiply that by 2.303. So we get 2.303 log it by I0 is equal to minus k1 t. That is log of it by I0 is equal to minus of k1 into t by 2.303. Now here k1 and 2.303 are the constant terms. So we can introduce a new constant. So we can write that as log of it by I0 is equal to minus of k dash into t. T is the thickness of the medium and k dash is a new constant that we replace instead of the k1 and 2.303 being both the constants. So again taking the logarithm on the right side. See, if we take natural log to the right side, we write e to the power of the term on the right side. But when we take log to the right side, we write 10 to the power the term which is present on the right side. So we want to remove log, we take log on right side. So it is it by I0 is equal to 10 to the power minus k dash into t. Rearranging the terms, we get it is equal to I0 into 10 to the power minus k dash t. So this is again the mathematical expression of Lambert's law. Next we will take the Beer's law, and then we will combine these two laws, which forms the basis or the principle of the colorimetric analysis. So now let us see the second law, that is the Beer's law. Beer's law indicates a relation between the absorbed light and the concentration of a solution. So this law states that when an absorbing substance is in a gaseous state or it is dissolved in a transparent solvent, the absorption coefficient K is directly proportional to the concentration C. Or in other words, we can state the Beer's law as when a monochromatic beam of light is passed through a homogeneous and transparent medium, keeping the thickness of the medium constant here, the rate of decrease in the intensity of the transmitted light with the increase in the concentration of the absorbing solution is directly proportional to the intensity of the incident light. So here we will focus on the concentration of a solution, keeping the thickness of the medium constant. Okay, let us understand this with the diagram as shown. Here we can see the series of the solutions taken where the concentration is increased from the first measuring flask to the second, third and fourth and fifth. So finally the measuring flask number 5 has more concentration. So as we see the concentration is increased, that is the color of the solution is increased. Say for example, we have taken here is 0.02 molar of the concentration of a solution, increased to 0.04 to 0.06 to 0.08, and finally we have 0.1 molar concentration. So as we increase the concentration, the color intensity of the solution increases, and hence what Beer law says is that as the concentration increases, the absorbance value will also increase. So mathematical expression of a Beer's law can be given as minus di by dc is directly proportional to I. According to the statement that is given, the rate of decrease of the intensity with the concentration is directly proportional to the incident radiation I. So there is a decrease, so we write minus di by dc is directly proportional to I. So this is equation number 1. Now removing the proportionality sign, again we get minus di by dc is equal to K2I, where K2 is the absorption coefficient, a proportionality constant that we have introduced. I is the intensity of the incident light and C is the concentration of the absorbing solution. So final equation that we get is minus di by I, taking similar terms on one side, it is equal to minus K2 into dc. Integrating the above equation within the limits as we had done in the Lambert's law, from concentration 0 to concentration C and from the incident radiation I naught to IT, we get integration of the equation from I0 to IT. Di by I is equal to K2 is a constant, so we take it out, concentration from 0 to C dc. Integration of this term we get ln IT minus ln I0. So as we know, we write ln IT by I0. So minus ln IT by I0 is equal to K2 into C. That we can write it as ln IT by I0 is equal to minus K2C, or we can write IT by I0 is equal to e to the power minus K2C. Okay, ln we take on the right side, so it is e raised to minus K2 into C. So rearranging the terms, we get IT is equal to I0 into e to the power minus K2C. This is the mathematical expression of Beer's law. Now let us derive the Lambert-Beer's law or Beer-Lambert's law. Now we say that the decreasing rate of intensity of the incident radiation is directly proportional to the thickness of the absorbing medium and the concentration. So when we combine both these laws, we say that the decreasing rate of intensity of the incident radiation is proportional directly to both the thickness of the absorbing medium as well as the concentration. So according to Lambert's equation, we have the equation IT is equal to I0 into E to the power minus K1 into T. According to Beer's equation, we have IT is equal to I0 into E to the power minus K2 into C. Now combining both the equations, we get a Lambert-Beer's law, that is IT is equal to I0 into E to the power minus K1 into K2 into C into T, that is concentration into thickness. So removing both the constant and introducing one new constant K, that is equal to K1 into K2, we get the mathematical expression for the Beer-Lambert's law, that is IT is equal to I0 into E to the power KCT. Now this again we can write in various terms, Lambert-Beer's law. as in we have the equation it is equal to I0 into e to the power minus kCt. This we can rearrange and write it as it by I0 is equal to e to the power minus kCt. Or if you want to write in the terms of ln, we write ln it by I0 is equal to minus kCt. See, it is the reverse term. We were in taking the ln on right side. Now we are taking ln on the left side. If we take ln, so we get the term minus kCt on the right side. Ln is to the base e, so it is e to the power minus kCt. So the this again equation we can write as ln I0 by it is equal to kCt. Okay, so my negative sign will be removed. So it is ln I0 by it is equal to kCt. If we want to write this in terms of log, we write log of I0 by it is equal to k upon 2.303 into C into T, concentration into thickness. Here the equation 3 or 4, we can say these are the mathematical expressions of the Lambert-Beer's law, and in the equation k is also expressed as epsilon, and this epsilon is dependent on the concentration units of the substance. That is, if the value of the concentration is taken in molarity, that is gram moles per liter, and the thickness of the medium is taken in centimeter, then epsilon is known as molar absorption coefficient or molar extinction coefficient. There are few terms again we can define from these equations, that we get it by I0 is the transmittance and log of I0 by it is the absorbance, or in practical terms we call it as an optical density that we measure using the colorimeter instrument. So these are the various expressions in which we can show the Lambert-Beer's law, and it is the full derivation for the equation. Thank you.